Hello everyone, this is Doug, and in this video we're going to talk about Graham's law of effusion and diffusion, and we'll talk about what effusion and diffusion are, what Graham's law actually is, and a couple of applications of it. So effusion versus diffusion. Effusion, with an E, effusion is the process of a gas escaping from a tiny hole in some container, and those gas molecules will escape going from high pressure to low pressure. So over here on the left, I have a little container, right? Here's where all the gas molecules are, right? These are supposed to be gas, whatever gas particle you've got. And then since we have gas particles inside, this would be the area of high concentration, and outside would be the area of low concentration. And so effusion is just the process of gas particles leaving through this little hole, right? Is the idea. They would be effusing out of a container, out of a balloon, out of a tire, out of whatever, just out. Diffusion doesn't require a vessel necessarily or a hole or anything like that. That's just the movement of any particle, gas or whatever, any particle from an area of high concentration to low concentration. And so in this example here, right, I have a before and after. So the top is before, the bottom is after. Where here I have an area of high concentration. Over here would be an area of low concentration. And what we're going to see is that over time, right, these gas molecules, they diffuse so that they're more evenly distributed, right? So now there's no concentration gradient. No concentration gradient anymore, right? It has the same concentration everywhere. There's no high and low place anymore. So before we had all of the particles in one place, they diffuse across the container, and now they're spread out all over the place, right? This would be like, again, if you had like a stink bomb, boom, you crack it. It's real stinky over here. No one can smell it on the other side of the room at first, but eventually those stinky molecules make their way across the room, so everyone smells a little bit of stinkiness. Lucky us. So effusion is when you have a gas leak out of a hole. Diffusion is where something just moves across whatever container it's in, whether it's a room or a cylinder or whatever, so that you have equal concentration overall. But both of them describe the movement of particles down concentration gradients from high to low. So Graham's law is sort of built on this observation that gases of different sizes travel at different speeds. And you may remember it if you don't, you should go back and watch this video, but I showed you a video on Dalton's law of partial pressures where I added two different gases. One was big, one was small. And if you go back and rewatch that video, the big ones moved more slowly and the little ones moved more quickly. And because of that, we can derive a bunch of things for Graham's law of diffusion and effusion. So if you have two gases in the same container, right, that means that the temperature is going to be the same for them. So this temperature is going to be the same. I'll put constant. Right? It's not like you can have two gases in one container and one can be like below 0 degrees Celsius and the other gas will be above 0 degrees Celsius when they're in the same balloon, right? They're going to be the same temperature. Now the thing is, right, so if they're at the same temperature, the ones that are smaller, right, so I'll say their mass is smaller, right? Remember that M is mass. Let me go ahead and write that for us. Right, the M is mass. This nu is the velocity or speed, technically velocity. And so if your mass goes down, which is what I was trying to say, right? So if your mass goes down, you get lighter, it must be that the speed goes up, right? Because you have the same temperature, you're at the same temperature. So if this value goes down, that value goes up. Or another way to kind of think about it with actual numbers, right, is if you have something like 100 is proportional to like 10 times 10, right? Which is what this is kind of like saying. If you're still at 100, but this first number goes down, say this first number goes down to 5, it must be that that second number has to go up, right? It has to go up. In this case, it has to go up to 20, right, for this to still be true. That's the same thing, right? Because these are constant. So that's kind of the analogy. For those of you who don't do a lot of like inversely proportional or directly proportional stuff, right? That's the idea. If the mass goes down here, if this whatever this is goes down, velocity has to go up. So as the mass decreases, the velocity increases. So small things move faster, large things move more slowly at the same temperature. And so I can just ask a little simple question like, which gas moves faster if in a balloon when you blow it up, right? Is it the nitrogen or oxygen, the two main components? Well, if I look at nitrogen, right, nitrogen's atomic mass is around 14. There's two of those, so it's around 28. I'm just doing real rough calculations here. Oxygen is around 16 times 2, right? So that's around 32 as far as their molar masses are concerned, right? How big are they? How much do they weigh? And so it looks like nitrogen here is lighter, and therefore it is faster. It's going to be moving faster. So which one is going to move faster? Nitrogen is going to move faster compared to oxygen. And then Graham's law, I'm not going to go through all this derivation stuff, but Graham's law basically just says that the rate of gas A divided by the rate of gas B is going to equal the square root of the molar mass of B divided by the molar mass of A. And these are not the same, right? So the A's on top here, A's on the bottom here, B's on the bottom, B's on top. If you want to look at the derivation, you can just go look that up in a book. I'm not going to go through all of it, or you can just Google it. But here's what Graham's law is saying, is that the rates, right, the relative rates of one another are related to the difference in their molar masses. How big are they? How much do those atoms weigh? And that's what we're saying before. Small things move faster, big things move more slowly. But we can actually calculate how much faster or how much slower. So let's say we have this question, right? So if hydrogen and carbon dioxide are placed in the same container, how many times faster will hydrogen effuse out of that container when compared to carbon dioxide? Right, so when compared to carbon dioxide. So this is a perfect example for me to use Graham's law on. So if I want to know the relative rates here, I need to figure out their molar masses. And so I'm just going to pick that my B here is going to be my carbon dioxide. And if I look at this, the molar mass of carbon dioxide is about 44. Again, I'm just kind of giving rough numbers here. Right, so this is for the molar mass of CO2. If I look at hydrogen here, right, I'm going to put the molar mass of hydrogen. That's going to be around 2. And so if I take that number, right, it's the square root of that number. Should give myself a little more space. That is going to equal 4.69. Or in other words, it's 4.69 over 1, right? So this is the relative rate. Right, remember, you got these rates here. This is the rate of A. This is the rate of H2 over the rate of CO2. So apparently hydrogen, H2, moves out 4.69 times faster than carbon dioxide. And that's all there is to it, right? Which should make sense to us, right? We should double check it. Double check our math, right? Hydrogen is smaller, therefore it should be the thing that moves faster, which is exactly what this number is saying, right? When I type this in my calculator, I got 4.69, which if I make it a fraction so I can see, right, that it's a fraction like this, I put the 4.69 up top over 1, so that equals the right thing, and then I get my rates. Let's look at another example. Here's one. In order to act as a warning, a smelly compound, hydrogen sulfide, is added to toxic phosphorus trichloride, which is quite toxic and annoying. If it takes 7.2 minutes for the smelly compound to get to you, that hydrogen sulfide, how long will it take for the toxic compound to get to you? So this is a diffusion question. The previous one was an effusion. This is a diffusion. There's no hole in a container. This is just talking about how quickly gases can diffuse across a space, namely to you breathing it. So if I do that, right, I'm going to go ahead and figure out my molar masses here. So if I take a look at these, the molar mass of, I'm going to call this one, let's do this. I'm going to call my RA the H2S. I'm going to call A the H2S, and I'm going to call B the phosphorus pentachloride, or trichloride, excuse me. Sorry, pentachloride is another compound. And so the molar mass, then I put the molar mass of the trichloride up top. So 137.22 is the molar mass for the phosphorus pentachloride. And it is 34.08. Again, you can look these up or just simply add them all up for the hydrogen sulfide. And that ends up equaling 1.59. But again, I'm just going to turn this into a fraction so that it looks like my R over R. 9 over 1, right? So that's supposed to be my rate of movement for my hydrogen sulfide, and this is the rate of my movement, my diffusion, for my PCl3. So again, my little thing moves faster. That makes sense. That should all be good. But now I got to turn this into like a time thing and how many minutes and whatever. So what I can do here is I can set this up so that it's like two different sort of equations. So like let's say we're talking about the hydrogen sulfide stuff. So this will all be H2S. All rates, right? All rates of movement are a distance over a time. And I can say the same thing for the other one, right? So PCl3, the rate of movement equals the distance over the time. That's just the rate of something, right? Like miles per hour or meters per second or something like that. But what this question is asking is how long does it take for that compound to get to you? So both of these compounds have to travel the same distance. So I know that the D's that I wrote here for both of them, the green D and the red D, those are going to be the same. So I'm going to set them equal to one another. So I'm just going to do a little algebra here. I'm going to multiply both sides by T so that those cancel. So in other words, I get that T, my time, times the rate equals D, and I'm going to do the same thing on the other side. Right? Multiply both sides by T. So I get T times rate equals, I'll put the D over here, right? So these distances are equal because the container to U is the same. So if those are same, then I can say that the time for the hydrogen sulfide times the rate at which the hydrogen sulfide moves is going to equal the time it takes for my PCl3 to move times the rate at which that PCl3 moves. And the real question, right, the question is saying, how long will it take, right? How long will it take for the toxic compound, the PCl3, to move? So I'm trying to solve for this. I'm trying to solve for the time of my PCl3. So I'm just going to divide both sides by the rates at which PCl3 moves. All right, so those cancel to give me no space. Let me do this. I'm going to get a little cramped, but that's okay. So the time that it takes for the PCl3 to get to me is going to equal the time that it takes the, let me just fill in the numbers. The time that it takes the hydrogen sulfide to get to you, which apparently is 7.2 minutes. That's what it said in the question. The rate at which it moves, I don't know what the exact rate is, but I know that it's 1.59 times faster than the rate of the PCl's movement, which we just said is 1. And if you solve for this, then you get that it's about 11.5 minutes, 11.4 minutes. So you'd first smell the stinky smell at 7.2 minutes, but then you wouldn't die until 11.4 minutes. That would be good to know. So that's another application of Graham's law of diffusion in this case. Those are the basic ideas. Do a couple practice problems. It's not a huge thing. It's not as important as the ideal gas law, but it is useful for some types of questions. So study up. Good luck.